Welcome to 205, Trig functions for obtuse angles. What's an obtuse angle? An obtuse angle means it's more than 90 degrees. So I'm coming along, and if I have an angle something like this, this would be an example of an obtuse angle. So far, of course, we've defined our trig functions using right triangles. That's supposed to be a right triangle. So these angles, they're sharp angles, right? So they're called acute angles. They have to be less than 90. And, you know, we would label a side, the opposite, the adjacent, and all that stuff, and we came up with a really nice way of defining trig functions for a right triangle. Our mission today is to define trig functions even if you can't make a right triangle out of it. Now remember, this whole SOHCAHTOA stuff that we've been playing with only works for right triangles. RT for right triangles, which means if we have an angle like this one with an obtuse angle, please don't even think about using SOHCAHTOA on this thing. No SOHCAHTOA. No do that. Don't use Pythagorean theorem for that matter, okay? All the stuff that we've been using so far does not apply unless it's a right triangle, and this is not a right triangle. That's not 90, that's not 90, that's not 90. That's not a right triangle. Don't use SOHCAHTOA, don't use Pythagorean theorem. So we're going to learn how to figure out trig functions for these obtuse angles. Let me get some of this stuff out of here now. Kind of messing up my page here. Okay. So we're going to do that, I promise. But first, I wanted to show you some more right triangles, actually. But they're so cool that I can't move on until we've looked at these three very cool right triangles. So one more page of right triangles, and then I promise we get to the obtuse stuff. So what does this say? This says a 3, 4, 5 triangle, and this is referring to the sides. You have side lengths of 3, 4, and 5, like this one. You have side lengths of 3, 4, and 5. Okay, why is that such a great triangle? That's just a darn practical thing to know, is that there is such a thing as a right triangle that has sides 3, 4, 5. If you're like framing a wall or something, and you've got this wall here, and then you want to install this wall, and you want to make sure that the walls are exactly at 90 degrees, well, what you can do is you can grab out your measuring tape, and you can come out 3 feet or whatever this way, and then you can make a mark, come out 4 feet this way, make a mark, get yourself a string or something that's 5 feet long, and have it, and then you move this wall back and forth until this string is exactly touching these 2 points here. This 5-foot string is exactly touching these points. It means you got a 3, 4, 5 triangle, which means you've got a perfect 90-degree angle. So it's a cool trick, cool thing to know. By the way, as long as we're on this triangle, see the problem with the problem, it's not really a problem, but the problem, so to speak, of this triangle is that this angle isn't anything really nice. Let's figure out what that angle is. So SOHCAHTOA for one more time here. So SOHCAHTOA, let's see, you could use sine, cosine, or tangent. Doesn't even matter, right? We know all the sides. I'm in the mood for a sine function today. So remember, opposite over hypotenuse is the sine function. So the sine of that angle is 4 over 5, which of course is 0.8. And so I just have to hit the shift sign, which is what that little symbol means, right? And I've probably said this before, but not the x to the minus 1. There is a button that has like a little minus 1 on it. Not that. Don't use that button. You have to use a shift sign all the time. Always, always, always. So turn my thing on here, shift sign of 0.8, and it turns out that angle is 53.1301 degrees. See, you wouldn't want to use like well, why would you anyway? The 5-foot string is better, right? I was going to say you wouldn't want to use a protractor to measure a 53.1301 degree angle and then sight to this point, but practically speaking, you wouldn't want to do that anyway. But the point I wanted to make is if you have a 3, 4, 5 triangle, well, it's a 53-degree angle on this side. I think I have a degree, minute, seconds button. Do you have one of those? Let's play with that. Push. So this is 53 degrees, 7 minutes, 48.37 seconds, right? 53 degrees, 7 minutes means 7/60ths of another degree, and this means 48.37 60ths of another minute, which is, since there's 60 minutes in a degree and there's 60 seconds in a degree, there's 3,600 seconds in a degree. So if you wanted to, you could, you know, go like this: 53 plus 7 divided by 60 plus 48.36 divided by 3,600 equals, and you end up with 53.1301 degrees. Okay. Or I suppose you could just hit the shift degree button, right? Right. Anyway, inserting some facts for you here that are cool to know. So there's that triangle. Everyone should know about it. That's all. If you're ever out building stuff or whatever, you should know about it. So it's cool. It counts as cool. That's why I call it one of the cool triangles. Now the next two triangles are pretty cool as well, and it turns out they're going to be very useful today when we get around to our mission, which is trig functions for obtuse angles. Let's take a look at these. These are the 45, 45, 90, which is referring, of course, to the angles here, right? That's a 45, that's a 45, and that's a 90. And also a 30, 60, 90. So this would be a 30-degree angle. Here's a 60-degree angle. Here's a 90-degree angle. So just scrolling up for a second. Over here, these numbers are referring to angles. So a 3, 4, 5 triangle, we're talking about the sides, but a 45, 45, 90 and a 30, 60, 90, we're talking about the angles. Anyway, I'm just going to give you some facts here. It turns out, if you got out your measuring tape, and let's say you measured this side, and let's also say that that side turned out to be exactly one whatever in length, 1 mile, 1 whatever, doesn't matter what it is. It's 1 in length. Well, this side here, I think you'll believe this. This side is the same, right? That's also a 1. And so what's the hypotenuse? Well, you could do a quick Pythag, square root of 1 squared plus 1 squared, and then take a square root. You end up with square root of 2. Now that's approximately 1.414 or something like that. But let's just use this exact value. That's a 1, that's a 1, that's a square root of 2. What this means is that you can define, what color am I on? This one. You can define, let's use this as my reference angle, right? You can define that the sine of 45 degrees is, hopefully by now you've had enough practice that these moves are almost natural to you, right? Opposite over hypotenuse, 1 over root 2. The cosine of 45 degrees, well, that would be the adjacent over the hypotenuse this way, 1 over the square root of 2. And then the tangent of 45 degrees, remember that would be opposite over adjacent like this, 1 over 1. I think I'll call that 1. Okay, so these are exact values, nice and exact, for the sine, cosine, and tangent of 45 degrees. When you hit the button on your calculator, it's probably going to say, oh, 0.707, oh, 0.707, 0.707, oh, it's a 1. Okay, but we're going to use these exact values today, so it's worth being able to figure this out. So the main thing to remember is, if it's a 45, 45, 90, these sides are 1, 1, and square root of 2. They're in that proportion. No matter how big or small you make that triangle, these sides are always in this proportion. This side and this side are the same. This side is a square root of 2 times the 1, or whatever. Here's another nice triangle over here. Back to blue. If you have a 30, 60, 90, that's one of those standard draftsman triangles, right? 30, 60, 90. And you happen to measure this side, and it happens to come out to 1. Let's just say that. If you call this the small side 1, okay, I love this part. The big side, the hypotenuse, is exactly 2. Isn't that something? It's a 1 to 2 ratio exactly. I always thought that was kind of cool. So if you can remember 1 to 2, then you can always Pythag if you forgot what this side is. I have it memorized. I'll just put it here. Square root, come on you, square root of 3. That's what that side is. And that's the thing to remember. A 1 to 2 to square root of 3 like this. The shortest side is a 1. The longest side is a 2. Square root of 3 is in between 1 and 2. How do you get that anyway? Well, you'd Pythag it, right? So if you called this an x temporarily, x squared plus 1 squared equals 2 squared, and you solve that. So x squared plus 1 equals 4, subtract 1 on both sides, x squared equals 3, take a square root, and guess what? You get square root of 3. Okay, so again, just try to remember these proportions. It's a 1, 2, square root of 3. That's the useful part. And what would the trig functions look like for this anyway? Well, let's guess we could do both sine and 30 and 60, but let's focus on the 30 for now. So the sine of 30 degrees would be opposite over hypotenuse, 1/2, exactly a half. Your calculator says 0.5, of course. The cosine of 30 degrees, adjacent over hypotenuse, root 3 over 2. Your calculator would say about 0.866 or something, okay? But it's the exact value is root 3 over 2. And the tangent of 30 degrees, well, opposite over adjacent like this, we're talking 1 over the square root of 3. And your calculator would say, I don't even know what your calculator would say. Let me figure out. What does my calculator say? My calculator says 0.577. I hope yours does too. By the way, if it doesn't, make sure you're in degrees mode. It's hard for me to believe that you could have made it this far without being in degrees mode. But anyway, make sure your calculator is set to play with angles in degrees. So that's our angles for the 30 degrees, sine, cosine, tangent of 30 degrees. And this is kind of nifty. Now let's, maybe in a different color. Now let's put our point of reference over here at the 60. So now, what's the sine of 60? Well, from here, this would be the opposite. So opposite over hypotenuse is, guess what? Root 3 over 2, which is 0.866. So that was the cosine of 30. Turns out the cosine of 30 is the same as the sine of 60. Ain't that something? You might be able to anticipate this part. Cosine of 60 degrees is what? Well, if I'm up here, I want to do my adjacent over hypotenuse. So that would be a 1/2. Can you dig it? This has a name. It's called the cofunction theorem. We don't care about that name or anything, but it's cool to know. The cosine of 30 is the same as the sine of 60. What makes the 30 and 60 special? They add up to 90 degrees. So like, if you had the sine of 40, that would be the same as the cosine of 50. I invite you to try it. These two angles add up to 90, so the sine of one is the same as the cosine of the other. It's just cool. You'll run into that just at random. Tangent of 60, well, what's that? That would, see, this time, this is our point of view, so this is opposite over adjacent. We'd be going that way, so that would be, actually, that would be square root of 3, which is like 1.732, something. So, anyway, it's, like I say, the main thing to remember is these ratios of the sides. A 1 to 2 to square root of 3 ratio, right? You don't have to memorize any of this stuff. You don't have to memorize. I wouldn't cross it out. It's nice. I'm not going to cross that out. It's too nice. But the main things to remember are the proportions of the sides. Okay. So now that I've shown you the 3 coolest right triangles in the world, we need to move on to today's mission, defining trig functions for obtuse angles. Remember, we want to go beyond right triangles. We want to have obtuse triangles. Now, we'll start slowly. See, we'll start slowly. How many have I got here? 1, 2, 3, 4, 5, 6. Okay, 6 examples should do it for us. So, what's this say? Use reference triangles to define trig functions for any angle up to 360 degrees. For any angle up to 360 degrees. So that's why we have a circle here. We're going to use, this is called the unit circle, but you don't have to call it the unit circle. Usually unit circle, just so you know what the phrase means if you go a Googling or YouTubing or whatever, unit circle means radius equals 1. I don't really do that. I don't limit myself like that. I'm like, I don't care what it's a circle. That's all I care about. So, okay, what do we got here? We got an angle. Now, you might guess what angle I meant to draw. I meant to draw a 30-degree angle. So we're defining trig functions for a 30-degree angle on the unit circle. So remember, this is 0 degrees at the right, and you're supposed to spin counterclockwise, so that would be 90 degrees. So 30 degrees is right in there somewhere. So there's our 30-degree angle. Now, at first, this is not going to be very surprising. What do I mean by reference triangle? What I mean is drop a plumb line from here straight down to the x-axis. There. Okay, cool. Now, since that's a 30, 60, 90 triangle, do you remember what the dimensions are? The relative dimensions? Remember, short side is 1, long side is 2. This side is the square root of 3. Now, I'm going to give you new definitions for sine, cosine, and tangent. We could still do opposite over hypotenuse and all that stuff. We could. It's a right triangle, right? Yeah, we could do it. But I'm going to give you these sort of algebraic definitions. The sine is y over r. The cosine is x over r. The tangent is y over x. Now, I didn't really do anything different except write it a different way. If you look at the 30-degree angle and you ask what's the sine, you would go opposite over hypotenuse this way, right? Well, this is like a y-coordinate here. What is that y-coordinate, by the way? That y-coordinate would be 1 because, see, it has a height of 1. So that's 1 over. Now, this would be the x-coordinate, by the way. So that's the x-coordinate. That's the y-coordinate. And this thing here, the hypotenuse, we call that the r, which is like the radius of the circle, which the way I've drawn it, it's not a unit circle. A unit circle has a radius of 1. The circle I drew has a radius of 2. That's okay. I'm okay with that. So 1, 2, square root of 3. And so sine is y over r is 1 over 2. Boom! Which is the same, again, as opposite over hypotenuse, using this as a reference angle, is what we actually call it. Cosine is x over r. So you grab your x-coordinate, right there, square root of 3. You grab your r, the radius, and 2. Boom! You're done. Same thing you would get if you did adjacent over hypotenuse. Tangent, y over x. Well, the y, it's right there, it's a 1, and the x, it's right there, it's a square root of 3. So this is front and center right now. Maybe it gets a box or something. Nice big blue box. These are our new definitions for sine, cosine, and tangent. You use these for a unit circle. Use these when what? When using a unit circle. I'm not going to say unit circle because mine has a radius of 2. When using circles, let's put it that way, to define trig functions. So use these, y over r, x over r, y over x, if you're going around a circle to define your trig function. Which, for the next one, again, we still don't have to for this one, because if I were to drop the perpendicular, and by the way, always to the x-axis. Always drop a perpendicular. Think of gravity, right? Which way does gravity go? It goes down. Always drop a perpendicular to x-axis. Just like a plumb bob. The plumb bob. Okay, so let's put that in, like, let's circle that with like red or something, because that's like important. We'll use this fuchsia color. That's so important. And I want to point that out because a lot of times on the homework, and it makes me really sad, but on the homework I'll see somebody go like this. And I'm like, no, you don't go sideways. Gravity is not horizontal. Gravity is straight up and down, right? Do the gravity. Hang the plumb bob. Boom, there you go. Now, can you guess what angle I was thinking when I drew that? I was thinking 45. Thus, we have a 45, 45, 90 triangle. So you remember what your dimensions are, your relative dimensions. You say, well, those sides are the same. Just call them 1, 1, and this would be the square root of 2. So you can define the sine of 45 as y over r, which is 1 over the square root of 2. Because, again, that's our y-coordinate, right? This is the r. Maybe I'll write that on there just for reference. This is the y-coordinate. It's the y-coordinate because you go up 1 to get to here. You go over x to get to this point, so that's the x-coordinate of the point. And then this is the r. It's the radius of the circle. In this case, it's a circle with a radius of square root of 2. I don't care what the radius is. See, I don't limit myself like that. But anyway. So we got the sine of 45. Of course, we knew that, but let's keep going. Cosine of 45 would be x over r, which would be 1 over the square root of 2. And then the tangent of 45 would be y over x, which would be 1 over 1, which is 1. I'm going to scroll up just to make sure these are the same things we got before. Yeah, same things we got before. 1 over square root of 2, 1 over square root of 2, 1. Yep. it's all nice and consistent. Oh man, I'm still in the first quadrant. I'm still in the first quadrant. Look at this. I want to get out of the first quadrant, but I guess we got one more. So you drop your plumb bob down to the x-axis. Gravity. Do gravity. Don't go sideways. Gravity. This is a right triangle. This, of course, I meant to make a 60-degree angle. So my y-coordinate, maybe I'll label it this way. I don't think I want to label it this way. Just what are the relative dimensions of these sides? Well, remember, with a 30, 60, 90, the shortest is a 1 and the longest is a 2. Call that square root of 3. So this, get back to green or something, this is our y, this is our x, this is our r, and so I can define my trig functions quite quickly. So the sine of 60 is y over r is root 3 over 2. Yep. The cosine of 60 is x over r, which is 1 over 2. Yep. And the tangent of 60 is y over x, which is root 3 over 1, which is root 3. Okay, cool. Let's get out of the first quadrant. Here we go. Now we're talking. Now we're talking fun. So what's going to be different here? Well, I'm still going to drop the perpendicular to the x-axis. P.S. That's called a reference triangle. And I'll show you why it's called a reference triangle in a minute. And this here, this angle here, and that's called the reference angle for the reference triangle. Okay, let's not worry about this right now. I do want to throw those terms out there because you'll see them all over YouTube, all over Google. They're everywhere. That's where they go. So that's called the reference angle. Now let me get this line out of the way. Okay, what are we going to do? We're going to say that's a 45, 45, 90 triangle. And the sides have relative dimensions of 1, 1, square root of 2, right? Here's what's different. Come on, you. Okay, this is different. Remember that x is positive when you go this way, and x is negative when you go this way? Come on. Well, that means that this is not a 1, it's a negative 1. The x-coordinate here is a negative 1. Notice y is up, that's still positive 1, that's okay. And by the way, the r is always positive. Just keep that in mind. When you have a triangle and you label the r part, the radius of the circle part, that's always positive. Radius is just a measurement that's just always positive. But x and y coordinates, they're not always positive. In this case, we have a negative x coordinate. So that changes our arithmetic a little bit. So let's crank out our functions. So sine of, now that's the reference angle, but this is the angle I was talking about here. This is where we get sine, cosine, and tangent. So that's a 45 reference angle, which is what we use to figure out what the relative dimensions of this triangle is, the reference triangle. But the angle that we're talking about here really is this one, which would be, let's see, 180 minus 45. This would be a 135 degree angle. So we're actually using this construction to define the sine of 135 degrees, which again will be y over r. So take your y, which is 1, take your r, which is square root of 2, it's 1 over square root of 2. Yep. Use this to define the cosine of 135 degrees as x over r. So x over r, there's the x, there's the r, not that one. So that's negative 1 over square root of 2. Negative 1 over square root of 2. And then the tangent of 135 degrees is going to be y over x, which is, well, let's get this out of here. Y over x is going to be a 1 over a negative 1. 1 over negative 1, which is, really, you should just write negative 1. So notice two of our trig functions come out negative. And that's the main thing that's happening when you rotate around the circle. You'll still have the same kind of standard, if you're at a standard angle, like, you know, like if you have a standard reference triangle, I should say, like a 30, 60, 90 or a 45, 45, 90, you're still going to get the same kinds of 1 over square root of 2's and stuff, but sometimes they'll be negative. It depends on whether your x or y is negative. Okay, that's the main difference, is getting the signs right, S-I-G-N, signs right. Okay, so this is really the page that has the meat on it, right? Okay, here we go. We're in the third quadrant now. So what angle is this? This, I meant for, well, let me erase this part for a minute. Let's put our reference angle in there. I meant for this to be a 30-degree angle. Drop my perpendicular, right? There's my reference triangle with the reference angle of 30 degrees. So this is a 30, 60, 90. So the theta here that we're defining our trig functions for then would be, you always start at the x-axis, that's always 0 degrees. You always go counterclockwise, and you come around like this, boom. So I went 180 plus 30. So this is actually a 210-degree angle that we're defining our trig functions for, by using the reference angle of 30 degrees set up like that. Now, first I just put the dimensions in here, or the relative dimensions in here. It's a 30, 60, 90. The short side is a 1, the long side is a 2, this side is a square root of 3. And then I worry about, well, which one of these things is negative? So remember, r is never ever negative, but this is a negative x-coordinate for sure, and actually this is a negative y-coordinate as well. So both our x and y's are negative. We still define the trig functions in pretty much the same way. We say, well, the sine of 210 degrees, in fact, it's exactly the same way. You take y over r, which would be take the negative 1 over 2. So the sine is negative half. The cosine 210 is, well, in this case, you would want to take the x over r, which would be negative root 3 over 2. So the cosine is negative as well. And then, to find the tangent of this 210-degree angle, you would do y over x. That's what you always do. In this case, y over x is negative 1 over negative square root of 3. The negatives cancel, so that actually comes out to be positive, right? Because you have a negative over a negative makes it positive. 1 over square root of 3. Alrighty. This one, I meant to have a reference angle here of 60 degrees. I invite you, have you caught on? I invite you to draw the reference triangle, figure out what the theta is that we're actually defining our trig functions for, and figure them out. What is the sine, cosine, tangent of that theta? Pause. Come back. Okay, reference triangle. Remember, it's all, I guess this time it's anti-gravity, but it's always a north-south for your. Drop a plumb line. I guess you have to put the plumb line from the x-axis down to here. Just never go this way, okay? Just never, ever, ever go that way. It's always a straight up down. So there's our reference triangle. That's a nice 90. And let's see. On a 30, 60, 90, the short side is a 1, the long side's a 2, and that's a square root of 3. Which of these things is negative? Well, the x-coordinate is a positive 1. That's fine. But the y-coordinate is a negative square root of 3 because that goes down. Remember, r is always considered positive. Always, 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 always. So that's our relative dimensions. What's the angle that we're actually talking about here? You'd want to rotate this way. So that would be, well, let's see now here. If that's 60, then this must be 30. So I've rotated 90 to here, 180 to here, 270 to here, plus 30. This is a 300-degree angle. By the way, you could, if you wanted to, define it as negative 60 degrees, right? Because you're just rotating in the opposite direction. Come to think of it, you defined it as 300. You could also define it as 660, right? Because you can add 360 to any angle and you're pointing the same way. So anyway, so we're defining trig functions for every possible angle on the planet is what we're doing. So where are we? Oh, we just got to write our trig functions. What'd you just do? So the sine of, what are we at again? 300. The sine of 300 is y over r. The cosine of 300 is x over r. And the tangent of 300 is y over x. Okay, these are your definitions, your brand new definitions. Use them all the way around the unit circle. So let's see, y over r in this case is negative root 3 over 2. That would be the sine of 300 degrees. cosine is x over r. That's this over this. It's a positive 1/2. And then the tangent, whoops, the tangent is going to be the y over x. That's the y, that's the x. It's a negative root 3 over 1, which is just a negative root 3. There we go. Maybe just a closing comment. Another reason we call that a reference triangle, it's enough, I guess, to say, well, you know, you just get your relative dimensions that way. But you could also say, well, the sine of this angle on this right triangle would be opposite over hypotenuse. So that would give me negative root 3 over 2, which of course is what we got. But I find it easier to just say, it's y over r. Come on, man, y over r. So memorize these things or keep them handy as notes somewhere. This is how you define your trig functions going all the way around the circle. We can now define trig functions for any angle we please. It's a good thing.